On November 10, 2084, an astronaut standing on Mars could look up through a solar filter and see something remarkable: two tiny black dots, one slightly larger than the other, slowly gliding across the face of the Sun. That is Earth, alongside our Moon. When a planet passes directly between a star and an observer, we call it a transit. In the 17th century, astronomers timed these events from different spots on Earth. By measuring the tiny differences in when a planet appeared to touch the Sun's edge, they could use geometry to calculate the distance between the worlds, mapping the physical scale of our solar system for the first time. Today, we want to map planets far beyond our solar system, but trying to photograph a planet orbiting a distant star is a massive optical challenge. The blinding nuclear glare of the host star completely washes out the tiny dark planet orbiting it. To get around that glare, astronomers use a tool called a light curve. As you can see in this graph tracking overall brightness, we don't actually look for the planet itself. Instead, we look for a distinct drop in the line, a temporary dip that proves a planet has crossed our line of sight. This shadow data is currently our primary window into distant worlds. By decoding the exact shape, depth, and properties of that dip, we can begin to see whether it's a giant gas ball, a barren rock, or a prime candidate for life. The light curve's utility begins with its depth. Different sized planets block different amounts of light, so the size of the shadow reveals the exact physical dimensions of the planet. To calculate that, you only need to know the size of the host star. As this equation shows, the depth of the dip in the light curve is equal to the square of the ratio of the planet's radius to the star's radius. We can see this geometry at work with LHS 1140b, an exoplanet located 49 light-years away, sitting right in the middle of its star's habitable zone. Astronomers initially thought it was a dense, rocky super-Earth, but by combining its mass with the precise transit depth, the math revealed a much lower density than expected. The data shows this is highly likely to be a massive global ocean world, with up to 19% of its entire mass made of water. A simple two-dimensional shadow, recorded over a period of hours, gives us the math required to deduce the three-dimensional composition and habitability of a planet trillions of miles away. But finding water is only step one. The size of a shadow can't prove a planet is biologically active. To find living things, we have to look closely at the glowing rim of that shadow. In transmission spectroscopy, the planet blocks most starlight, but a tiny fraction passes through its atmospheric halo. Atmospheric gases absorb specific wavelengths, leaving missing gaps in the color spectrum, a chemical barcode revealing exactly which molecules are in the air. We are currently using the James Webb Space Telescope to point this technique at promising targets like TRAPPIST-1e. By scanning those barcodes, astronomers hunt for biosignatures, specific combinations of gases, like oxygen and methane, that shouldn't exist together unless biological life is actively producing them. There is a major complication, however. The stars themselves are violently active. Star spots and solar flares on the host star's surface can contaminate the reading, scrambling the delicate light data before it ever reaches our telescopes. Reading the rim of a shadow is a brilliant workaround, but relying on transits means our search for life is constantly bottlenecked by the messy, unpredictable noise of the stars themselves. To bypass that stellar noise, astronomers have realized they need to stop waiting for planets to cast a shadow. Instead, we have to find a way to block the star ourselves. This is the exact problem NASA's upcoming Habitable Worlds Observatory is being built to solve. The core of the observatory will feature an advanced instrument called a coronagraph. By physically placing a tiny, opaque mask inside the telescope, it creates an artificial eclipse. This suppresses the host star's glare by a factor of 10 billion, revealing the incredibly faint planets orbiting right next to it. Once that glare is removed, a back-end instrument called an integral field spectrograph takes over. It processes this newly revealed light and captures individual chemical signatures from multiple planets simultaneously, all without ever needing a transit. For 400 years, we have relied on planets stepping into the light to cast a shadow. Now, by mastering the physics of starlight, we are building the tools to step into the dark and find the fingerprints of life ourselves.